Hello everyone. I hope your semester is going well. I know it's a little bit rough now that we are at the climax of the semester, but we will get through this. Anyway, so in this week's experiment, we are talking about determination of the equilibrium constant for a metal and a ligand in a coordination complex. So our coordination complex here would be the iron thiocyanate. It has the 2+ charge. And so we are looking at determining the nature of equilibrium between the chemical species leading to this reaction, and we will then calculate the equilibrium concentration of the various species that will help us to obtain the equilibrium constant. And finally, we will be able to relate the equilibrium constant with the Gibbs free energy to determine whether our reaction is spontaneous or not. So just to go into the specifics, we have our two chemical species, our reactants, which is the iron 3+, and we also have the thiocyanate. So when these two reactants combine, they form a complex, which is the iron thiocyanate, and this complex here is red in color and it absorbs light at a wavelength of 460 nanometers. That is significant for this experiment. And so our objective is to determine the equilibrium constant for this reaction and then find out from the calculation of the equilibrium constant if the reaction favors the products or the reactants. And finally, we will realize that from the Kc value, we can calculate the Gibbs free energy that enables us to know if this reaction is spontaneous or not. Alright, so let's get started. Again, just looking at the expression for our reaction, we have here the iron 3+ combining with the thiocyanate, and then we have here our complex formed, and therefore the equilibrium expression is here in this equation, and this is also very significant for what we will be doing in this experiment. So how do we arrive at the equilibrium constant? Well, the equilibrium constant. First, you realize that we need the concentration of each species at equilibrium, the product and the concentration of the reactants as well. But how do we determine these concentrations when we don't have a way to exactly measure the concentrations? Well, we said that our product, the iron thiocyanate, it actually absorbs light at the wavelength of 460 nanometers, and by obtaining the absorption, we have a way of calculating the concentration of our product at equilibrium, and we should see how to relate these two concepts here. So Beer's law gives us a way of relating the absorbance value and the concentration. So you can see that it's directly proportional. And because we are interested more in the concentration value, we are going to use the ratio because we have a standard and we also have the samples at different concentration values in equilibrium. And that should help us to use this equation, concentration of our sample at equilibrium, and here the this C value stands for the concentration of the product, the FeSCN 2+. And here we have the concentration of the same, the product, that is obtained by mixing specific amounts of our reactants to obtain the standard concentration. And then we will multiply that by the ratio of the absorbance values for these two, the sample at equilibrium and also the sample of our standard. And just to give you, so these values were generated and you can find them in LogaPro, and the files will give you a table like this and a spectrum. But just to give you how to find the exact value of the concentration that you need, we say that you want to look at the wavelength of 460 nanometers. Let's just use the 460.3 for now. And the absorbance value that you will be using in this case, for example, is the 0.676. So you will receive files for the standard and then for the 5 different samples. And make sure that you are using this absorbance value, the 0.676, at the 460 nanometer wavelength. Okay, so I find this lab a little bit confusing, but once you understand how to fill in table 1, it should give you an idea of exactly what you need. So this slide is a little bit heavy. Other slides will walk you through step by step how to fill each point, but for now let me highlight the most important points. All right, so the first thing, we say that we need to calculate the initial concentrations of our reacting species, so the iron 3+ and then the thiocyanate. So you realize here that you have 2 values for your iron 3+, and this one only applies for the standard because you are going to use the 0.2 molar iron 3+ for your standard. But for the other varying concentrations that you use in determining equilibrium values, you are going to use the 0.002 molar. It's a much diluted concentration of the iron 3. And therefore, just think about when you are mixing the very high concentration of the iron 3+ with 0.02 molar thiocyanate, then you expect that the thiocyanate will be converted completely to the product. But with the equal concentrations here, they are going to partially form the product. And so you don't expect that all of the sodium thiocyanate, all of the thiocyanate is converted to the product. But anyway, just to begin, you will need the initial concentration of your species and then the initial volume, and this should be relatable to your final concentration of your species and then the final volume. So just to give you a quick example here, with the standard, you took 18 milliliters of, okay, let's leave this alone because this is a lot of it. Let's do the thiocyanate. So we took 2 milliliters of 0.02 molar thiocyanate. So the 2 will be the concentration times the the 2 will be the volume, and then 0.02 will be your concentration, and it should be equal to your unknown, which value should go here in this box, and then the volume will be, once you combine 18 and the 2, should give you the 20 ml. So that gives you, for example, this calculation here, and whatever value you get for your X, it should go in this column. So just make sure you are following what initial concentrations you use here so that you can arrive at the correct X value for both the Fe3+ and then the FeSCN-. And then you notice that the volumes for the standard is 20 milliliters, but the volume of your other solutions are just adding whatever you added together to get, for example, 5 + 1 + 4 is 10 ml. So instead of having 20 here, you would have 10. Okay? And then going to the next thing, here you need the absorbance values, and let me use right here. So the absorbance values, as I said before, you will get files on Logapro that show you a table like this. Just make sure you're scrolling down all the way to 460 nanometers, and sorry, let's erase that. So make sure that you are scrolling to the 460 nanometer wavelength, and this is the value. So for the standard, this will be the value that goes here, and these files are labeled so that you have solutions 1 through 5, and just make sure you're copying the right value of your absorbance into this column here. Alright, so that's done. And then when it comes to calculating the product, which is the ion thiocyanate, we have this equation that helps us to relate the absorbance and the concentration of our values at equilibrium, and also, you know, using the standard concentration that we have. So when we added the ion 3 plus, the 0.2 molar one, and also this thiocyanate, the 0.02 molar, we formed the product, which is FeSCN 2 plus, and this value here is similar to this value here, just because we are assuming that just for the standard, that all of the thiocyanate is being converted to our product, okay? But for the other samples, because we did not convert all of the sodium thiocyanate, all of the thiocyanate to the product, then ignore using the 0.2 molar Fe3 plus. Make sure that you calculate it using the right concentration values. Okay, so now that we know that the concentration of the thiocyanate here at equilibrium is this value here, which will be used for the rest of it. So this value you already have, and then to compare with the other samples, so you have, for example, this absorbance value of the standard. Make sure that you know what that is, and also the absorbance value of your sample, which would be any of this here, and that should give you the value of the FeSCN 2 plus that will go to this column. So the value that you get here is what goes in these columns. Just make sure that you're using the right absorbance values. This is constant, and this is also constant. So what will be varying in this equation is just for sample 1, it will have its own absorbance value. For sample 2, it will also have its absorbance value, and so forth. Moving on to the next thing, now that we have the concentration of the FeSCN, the product, then we need to calculate the concentration of the other species at equilibrium. And that means what you started with here, for example, or here, just going by the ion 3, so you have to get the value that you get here. For example, let's say, let's call this Y. The value that you get here, you will subtract it by the value that you get here. So this ion 3 at equilibrium would be the initial starting amount that you have minus the value formed here, and that should give you, for example, the value that you need for this box here. Okay, so just once you calculate this, just subtract it from that to get this value here. And the same thing when you are doing the thiocyanate, you begin here with the thiocyanate, and I will change the color for that so it's not as confusing. Let's do green. So let's do the Y again for the thiocyanate because you're interested in the final value here, thiocyanate, and then you subtract it with okay, let me delete this, never mind. So this will also apply because the product is the same. So you still subtract the X so that you can arrive at your concentration for the thiocyanate. And then finally, you have your equilibrium expression calculation here by taking the concentration of species at equilibrium, which would be this column here. So the values that you get here will go in here, and then the values that you get in these two columns will be what go here to the bottom. And that should help you find the value for the equilibrium constant for all your 5 samples. Okay, so this one goes more into the details of what I just highlighted as an important features for table 1. So this one gives you specifically with the initial concentration of your thiocyanate and how all of it is converted. So this is the exact amount, and all of it is converted to the complex that is formed. So that's why you have 0.002, which is the same value that you had here for the thiocyanate, because all of it is being converted here. And this will be the concentration of your standard that applies in the calculations for all the other equilibrium species. And then just the other solutions, as I had talked about before, how you will need to use the M1V1, considering sample 3. This is exactly how to determine the concentration of your iron and also the thiocyanate. Just walk through that to make sure you get the right number. And just helping you to get the C of the sample, as I mentioned before, would be using the sample 3 again. Just use this PowerPoint slide here to help you arrive at this number, then you'll be right on track. And so we say that so this is also just taking you through the step of determining the concentration of Fe3 plus in equilibrium, and you have the ICE chart, and I just told you, for example, you just need to subtract the initial minus the concentration of your FeSCN2 plus at equilibrium, which you find by doing the concentration of the standard times the absorbance ratio for the sample and the standard, and subtracting these two will get you here. So also use run 3, for example, to help you stay on the right track. Now, once we have obtained the concentrations of species at equilibrium for our product and reactants, just plug and chug your numbers into the equation, and that should help you find the number for the equilibrium concentration. A number that is greater than 1 means that the products are favored, so the reaction will proceed forward, and vice versa. If you have a less than 1 value of Kc, that means that your reactants are being favored and the reaction is not going forward. Alright, so finally, is the reaction spontaneous or not is the concept of Gibbs free energy. So all the calculations in the table led to the obtaining of the equilibrium constant value, and this will be just plugged into this equation. R is a constant, and this is the value of R, and in this equation, this liter times kilopascals is also equal to a unit of energy, which is joules. and therefore you can just leave this in this unit or just substitute it with joules. But because you are multiplying, this is the unit of R, for example, with the joules by Kelvin mole, you need the temperature of the reaction, and which will be given to you. It was about room temperature, about 25 degrees Celsius, but you need to convert that number to Kelvin. And once you obtain the Kelvin, the K's will cancel out and you will have a number of joules per mole, and this is a constant, so there's no unit there, and your Gibbs free energy should be in terms of joules per mole. Alright, and so once you have a negative, if your delta G is negative, then you know that products are being favored because they're at a lower energy than reactants, and vice versa.